Ladies and gentlemen, dear colleagues, welcome. We are here again after vacations, and let me ask Mike Pinedo to introduce the 46th speaker of our scheduling seminar.
Okay, welcome to today's scheduling seminar. Kan, is your video on?
Yes. Can you hear me?
I can hear you, but I cannot see you.
I see the presentation. It should be okay. Yeah.
I see the presentation, but I don't see Kan's face.
Ah, the Kan's face. Okay.
Let me check.
Should put video on.
Can you see me now?
Yeah. Now I can see you.
Okay.
And now it's off again. The moment you put your, you share your screen, I don't see your face.
Yeah, I shared my screen in my iPad, so I guess when I share it, the video is turned off by itself.
Oh, so we won't be able to see you talking.
Oh, then let me try on my computer.
Okay.
Wait for a moment. Oh, I cannot use Zoom in my computer. It is out of date, the version. So
okay, so then we have to do it without seeing you. Okay.
Without seeing his face, that's okay.
Without seeing your face, okay. Let me then start introducing you. Well, today is our speaker, Fang. Kan has received his originally from Purdue University under Nelson Wuhan, and after that he immediately went back to mainland China, and he became, I think maybe 7-8 years ago, a professor at Tianjin University and in their business school. And he is mainly in deterministic scaling, and I think he is probably the world's expert in applying Benders decomposition in deterministic scaling. So if anyone wants to see if Benders decomposition would work on his or her problem, you should contact Kan, because he is a specialist, the specialist in Benders decomposition and scaling. Okay, Kan, please go ahead.
Okay, thank you, Mike. Hello everyone. I'm Fang from Tianjin University, and it's my great pleasure to present a talk at a global scheduling seminar. And I would like to thank the organization from the board, and also thank Mike for his invitation. Today, I will present one of our recent work on single machine scheduling in additive manufacturing with the two-dimensional packing constraints. And this is a joint work with Mao Zaofang, Fu Enyue, Huang Die, and Chen Ling. I will first give a brief summary of my talk. So in this work, we consider a single machine scheduling in additive manufacturing with two-dimensional packing constraints. And for simplicity, we also call this problem as the SAM2DP problem. And to solve this problem, we developed an approximation algorithm and also a combinatorial Benders decomposition algorithm. For simplicity, we call this algorithm as the algorithm CBD. And the computational experiments show that our proposed algorithm CBD performs well in solving such problems. Okay, in recent years, additive manufacturing, also commonly known as 3D printing, has been widely used to create objects by adding materials layer by layer and from 3D digital model files. The additive manufacturing has several advantages. For example, it can shorten the product development cycle, reduce material loss, and create highly complex geometries without molds. According to a recent report by Grandview Research, the global additive manufacturing market size is expected to rise from $1672 billion in 2022 to reach a value of more than $76 billion by 2030 at a compounded annual growth rate of 20.8%. And until recently, the additive manufacturing has been an important part of the fourth industrial revolution. So although the additive manufacturing has the above mentioned advantages, it also has several obvious disadvantages. For example, the processing speed of additive manufacturing is usually quite slow compared to the traditional subtractive manufacturing. Meanwhile, the equipment and the materials for additive manufacturing are usually at high costs. And the additive manufacturing also usually needs some additional pre- and post-processing procedures, such as cleaning, sintering, heat treatment, and so on. To speed up the processing of additive manufacturing, there have been several AM technologies that can allow different parts to be processed simultaneously in the same batch. For example, the selective laser metering technology, SLM, or also known as the direct metal laser sintering technology, the DMLS technology. So in this work, we mainly focus on the corresponding batch scheduling problem on a single machine with the DMLS technology, in which we assume that parts can be processed simultaneously without violating the two-dimensional packing constraints. And we also assume that parts cannot be vertically stacked. So to illustrate, I will give a figure from the work of Li 2017 to explain the production process of SLM or the DMLS technology. So before we start, we first need to perform a series of pre-processing operations. For example, the data preparation, the filling of powder material, so the gray part here, and the adjustment of AM machines. And also the filling up, we need to filling up protective atmosphere. And after that, we also need to determine one or more parts that can be produced simultaneously in the batch. Then, after finishing the pre-processing operations, we have two procedures. The first one is that the additive machine will generate thin powder layers, and which is typically with a thickness between 20 micrometers to 60 micrometers. And then the thin powder layer will be loaded from the powder delivery platform, which is the left-hand side, to the build platform in the right-hand side. After that, a high-power laser beam will be used to scan the powder material to identify the powder material. And by using these two processes alternatively, the final object will be produced will be created layer by layer. And after all the parts in the batch have been produced, we need to take out the objects from the additive machine. And after that, we will need to clean the machine and also replace the filters. So that means in order to process the next batch, we need a setup time. So from the above introduction of the DMLS technology for its production process, we can see that the production time of a batch is affected by the set of parts allocated to this batch. In particular, the following three factors will play the most important role in affecting its production time. The first one is the maximum height of the parts. So for example, here we have several parts in the build platform, and the highest part will play an important role in affecting the production time. This height, the maximum height, will affect the powder layer iterations during the processing. And the second one is the total volume of parts. And this part will affect the scanning and the layer fabrication of parts. And finally is the machine setup time. So in this work, we will follow the formulation provided by previous researchers, including Li, Kuchkok, and Otkin and Butchin. So they all assume that the production time of a batch is the weighted sum of the above three factors. Now we will formally describe the SMSAM 2DP problem. In this problem, we are given a set of parts I equal to 1 to n, and each part I has a predetermined orientation, a length Li, width Wi, height Hi, and volume Vi. So in this case, we know that the orientation is determined, and we don't need to determine the selection of orientation for each part. And for the additive machine, it also has the corresponding length, big L, width, big W, and height, big H. And also it has a scanning time per unit volume, VT, recoating time per unit height, HT, and also a setup time between any two batches. So obviously we must have Li should be less than or equal to big L, Wi less than or equal to big W, and Hi less than or equal to big H. Otherwise, if a part does not satisfy this condition, then this part cannot be feasibly packed into the build platform of the additive machine. The objective of our problem is to minimize the makespan. So in order to solve this problem, we make some assumptions. The first one is that the geometry of each part is projected on the XY plane, and the minimum rectangle limits is used to place the part in the building chamber or building platform. And we call a batch is feasible if there is no overlap between the rectangular bounding boxes of any two parts. And we assume that once a batch is started to process parts, it cannot be interrupted until its completion. And obviously, the makespan is equal to the completion time of the last batch in the schedule. So in order to solve this problem, we mainly need to determine two decisions. The first one is the assignment of parts into batches. And the second one is that the position of parts in each batch. And to formulate this problem into an optimization model, we define the following decision variables. We define Xi, Yi as the coordinates of the front left corner of part I. For example, this is the building platform of the additive machine. And this is a part, the rectangle bounding box of a part I. Then the front left corner is this point, which is denoted as xi, yi. And then we also define ZB is equal to 1 if batch B is opened and 0 otherwise. And UIB is equal to 1 if part I is allocated into batch B and 0 otherwise. And then we also denote two variables to denote the relative position between part I and part J. So left IJB is equal to 1 if part I is located left of part J in batch B and 0 otherwise. And below IJB is equal to 1 if part I is located behind part J in batch B. And we also define HB as the height of batch B, CB as the completion time of batch B, and the Cmax is the makespan. So given this decision variable, we can construct the constraints. The first constraint is that each part I must be allocated to exactly one batch. So we can have a constraint like this, sigma UIB equal to 1 for any I belong to I. And the second one is that the height of each batch must be greater than the height of each part in this batch. So we have HI times UIB less than or equal to HB. And also we have each part cannot be placed outside the machine's platform in both horizontal, which we denote the width of the parts, or vertical, that we denote as the length of the parts directions. So we have Xi plus Wi should less than or equal to W plus M times 1 minus UIB. So this is these two constraints are also quite trivial since we have a part like this. So this is the front left corner of this part, Xi, Yi, and this is the Wi, this is the Li. So we must have Xi plus Wi less than or equal to W, which is the width of the machine. And then we have the fourth requirement. If two parts R and J are allocated into the same batch, they are not allowed to overlap with each other. So by using the decision variables of left and below, we can have the following three constraints. So the first one means that for any two parts, if they are processed in the same batch, then we know that at least one of these four decision variables must equal to 1. And the other two also describe the relationship between these two parts. And the fifth constraint is that batch B is opened if at least one part is allocated to this batch. So this is also obvious. And the sixth constraint is said that a batch can be opened only if its previous batch has already been opened. So we have a sigma UI B plus 1 should less than or equal to big M times sigma UIB. And the seventh constraint establish the relationship between the completion time of the current batch and the completion time of its previous batch. So this is the formulation that we have just mentioned, the three factors that can affect the production time of a batch. And finally, the final constraints define the makespan. That is, the makespan should be greater than or equal to the completion time of any batch. So according to our literature review, actually, until recently, additive manufacturing scheduling has been increasingly investigated by different researchers. And here are three that closely related papers also consider the scheduling problem in additive manufacturing with two-dimensional packing constraints. And also we can find about nearly 30 papers starting from 2016 and to 2033 on the scheduling, on different scheduling problems in additive manufacturing. And these papers can be divided according to the problem types that they have investigated. For example, this S means that they only consider the scheduling problem, and NS means the problem that consider both nesting and scheduling problems. And also OAS means that they consider the order acceptance and scheduling problems. And this literature also consider the different objectives. For example, minimize cost, minimize makespan, and minimize tardiness or lateness, and so on. And they also consider various manufacturing environments and also constraints. For example, they consider different machine environments, including single machine, parallel machine, and also consider some other environments like processing alternatives and setup times, and also, for example, build orientation. And due to the inherent complexity of such problems, actually most of the work on scheduling in additive manufacturing mainly focused on the design of heuristic or meta-heuristic algorithms. And to the best of our knowledge, there are no studies that have been investigated on solving scheduling problems in additive manufacturing with two-dimensional packing constraints. And in this work, we mainly focus on the design of approximation algorithm and also the design of exact algorithm for such problem. So we first provide an approximation algorithm for our considered problem. So obviously, in any optimal schedule for the SM-SAM2DP problem, there must be no unforced idleness between any two consecutive batches. Now, we let PB as the processing time of batch B. Then the total processing time of all batch P is P equals the summation of PB and equals the first term, which describes the total scanning time. And the second term describes the total recording time. And the third term describes the total setup time. So from this formulation, we can see that the total scanning time actually is a constant because the total volume of all the parts will keep unchanged. And therefore, we know that the optimal makespan only depends on the total recording time and the total setup time. And the total recording time, it is depend on the maximum height of parts in each batch. And the total setup time actually depends on the number of batches that has been opened to pack the parts. Now we suppose that sigma star is an optimal schedule in which the total number of batches opened is T. So suppose sigma is the optimal schedule and we have some parts in each batch. And the total number of batch is T. And for simplicity, we also assume that H1 star greater than H2 star and greater than HT star, where HK star is the height of batch K. So the maximum height of batch 1 has the highest height, and then so on. So H1 star greater than here H2 star, and so on, and this HT star. And the makespan of the optimal schedule now can be calculated by this formulation, which is VT times sigma VI, and this is a constant, and HT times sigma HK star, and ST times T. So by this formulation, we can see that if we want to design an approximation algorithm, we should design a feasible packing solution so that the HK star here and T here has some relationship with the obtained packing solution, which also can be divided by different batches. And for each batch, it has a corresponding height for this batch and also the number of batches. So we need to establish the relationship between these two values and the values in the obtained feasible packing solution. So one idea that we use is we first divide all the parts into 3 groups. So in group 1, which we denote as I1. I1 is the set of parts that has Wi less than or equal to 1/2 W and Li less than 1/2 L, big L. And I2 is the set of parts that has Wi greater than 1/2 W. And I3 is the set of parts that has Wi less than or equal to 1/2 W and Li greater than 1/2 L. So from this definition, we can see that for any parts in group I2, they cannot be placed together in the horizontal direction because each Wi is greater than 1/2 W. So they can only place like this. They cannot place like this. And similarly for I3, they cannot be placed vertically together. So we cannot have one part here and the other part here. So they can only be placed, packed like in this way. So now we let Ni be the number of parts in each group Ri, and we sort the parts in each group in non-increasing order of their heights, and denote JKi as the case part in group Ri. Then that means that Hj1i greater than Hj2i and so on, and until Hjnii. So the idea of our algorithm, of our approximation algorithm, is that we use some greedy idea to pack all the parts in each group separately. For example, for group I1, we check when a new part needed to be packed. Then we check the total area of the current batch. And if the area of the new part plus the total area of the current batch is still less than or equal to 1/2 W times L, then we put this new part into the current batch. And otherwise, we close the current batch and open a new batch. Then we put this new part into the new batch. And similarly, for group 2 and group 3, for group 2, if we have a new item, a new part, then we first check whether the total length of the current batch plus the length of the new part is less than or equal to L. If so, then we put this part into the current batch. Otherwise, we will close the current batch and open a new batch, then put this new part into the new batch. And for group 3, we use the similar idea, except that we now compare the value of W instead of the length. So obviously for group 2 and group 3, the packing method in this algorithm greedy pack. So we call this algorithm as algorithm greedy pack. So the algorithm greedy pack for group 2 and group 3, they obviously can produce feasible packing solutions. And then now we also need to verify that for group I1, it can also produce a feasible packing solution. So in order to verify it, we first need a theorem which is proposed by Steinberg. So let W bar equal to maximize Wi, where I belongs to I tilde. So I tilde means the number of parts that in group 1, and L bar equal to maximize I belong to I tilde Li, and A is the total area of these parts in I tilde. Then if we can verify that the 3 conditions where W bar less than or equal to W, L bar less than or equal to big L, and 2A is less than WL minus 2W bar minus W. Here is a function that denotes the maximized value of X and 0. So if these 3 conditions are satisfied, then it is always possible to pack all the parts in I tilde into the rectangle with width W and length L. So for group 1, since we assume that Wi is less than or equal to 1/2 W and Li is less than or equal to 1/2 L, so we know that this part must be 0 and this part must also be 0. And then, since each time we check if the total area of the current batch is still plus the new part is still less than or equal to 1/2 WL. So we know that this condition is always true. And these 2 conditions are also true. So for group 1, we know that the packing solution provided by algorithm greedy pack is feasible. And by these observations, we know that algorithm greedy pack can provide a feasible packing solution for all the parts. Now we start to establish the relationship between the number of batches opened by algorithm greedy pack and the number of batches opened by the optimal schedule. So we let Si to be the number of batches opened for each group II by algorithm greedy pack, and denote HKI as the height of the case batch in group II, also by greedy pack. Then we have this lemma. That is, we have S1 should less than or equal to 4T. So in order to prove it, we first need to notice that a new batch can be opened only if A, which is the total area of the current batch, and plus the area of the new part. If these two, the summation of these 2 values is greater than 1/2 WL, then we know that we need to open a new batch to put the new part into this batch. So this means that the total area of parts in any 2 consecutive batches must be at least 1/2 WL. So the total area of parts in II is at least S1 divided by 2 and times 1/2 WL. And also the total area of parts in I1 is at least T times WL, because T is the total number of batches opened in the optimal schedule. So the total area must be less than or equal to T times WL. So in this way, we can obtain a relationship between S1 and T. So we have 1/4 S1 times WL should be less than or equal to T times WL. So by removing WL from the inequality, we know that S1 must be less than or equal to 4T. And similarly, we can establish the relationship between the height of each batch by greedy pack and the height of each batch in the optimal schedule. So we claim that for any K greater than or equal to 0, we must have H 4K minus 3, 1 is less than HK star. So in order to prove this lemma, we first check when k equal to 1, then this is obviously true, as h1 star, which is the height of the first batch in the optimal schedule. It must be the largest height. So this is obvious true. Then as we know that we have sorted the height of each batch in the feasible packing solution, we have h11 is greater than or equal to so on, and greater than or equal to h4k minus 5, 1, and greater than 4k minus 4, 1, and greater than 4k minus 3, 1, and so on. So we check the total area of the first 4k minus 4 batches, which is obtained by algorithm greedy pack. So the total area of the first 4k minus 4 batch must be at least 2 times k minus 1 times 1/2 WL. So, and in this way, we know that this is equal to k minus 1 WL. Right? Okay, this is because for any 2 consecutive batches, the total area must be at least this one, right? And the parts in the first 4k minus 4 batches cannot be fully packed into k minus 1 batch in the optimal schedule, since the total area is at least k minus 1 WL, means that the k minus 1 batch has already been fully packed. So in this way, we know that there must exist one part I prime in the first 4k minus 4 batch that will be packed into a batch between batches k and t in the optimal schedule. Then we know that hi prime, since it is a part that in the first 4k minus 4 batches. So we have hi prime is greater than or equal to h4k minus 3, 1, since h4k minus 3, 1 is here. And the I is belong to the previous 4k minus 4 batches. And also we know that hk prime is greater than or hi prime. So we have hk prime greater than hi prime greater than or equal to h4k minus 3, 1. So by using this result, we can summation, for example, h11 plus h21 plus h31 and plus h41, and so on. And for every 4 parts, we can sum them together, and we can obtain that sigma k equal to 1 to S1, hk1 is less than or equal to 4 times sigma hk star. Then for group 2, we can obtain similar results, except that we now have S2 less than or equal to 2t, not 4t anymore. And S3 is also less than or equal to 2t. So the observation, the proof of this lemma is similar to the proof of the first lemma, S1 less than or equal to 4t. So the main idea behind this lemma is that any of 2 parts in I1 can only be packed together if their total length is not greater than L. And a new batch needs to be opened only when L plus Li greater than L. So L tilde plus Li greater than L. And the total area of parts in any 2 consecutive batches must be at least WL. So by this way, we know that the total area of parts in I2 is at least S2 divided by 2 times WL. And similarly, we can have this relationship. So we obtain S2 less than or equal to 2t. And a similar result hold for group 3. And then we have this similar lemma for group 2 and group 3. So for any k greater than or equal to 2, we have h2k minus 1, 2, less than hk star. And for hk 2k minus 1, 3, also less than or equal to hk star. So the proof is quite similar. We just noticed that the total area of the first 2k minus 2 batch must be at least this value. That means that the parts in the first 2k minus 2 batch cannot be fully packed into k minus 1 batches. And then we can claim that there must exist one part I prime will be packed into a batch between k and t in the optimal schedule. And then we can obtain a result like this. So similarly, we can also prove the result of this one for group 3. And then with summation for both values, then we can obtain a relationship between the height of each batch in the gradient algorithm and the height of each batch in the optimal schedule. So by combining all the results in this lemma, we can claim that the approximation ratio of algorithm gradient pack is at most 8. So the proof is also quite straightforward. We denote sigma as the schedule generated by algorithm gradient pack, and then C max sigma be the corresponding makespan. Then we have C max sigma is equal to this one plus this one and plus this one. So since each of them has a relationship to the value of sigma hk, so we know that this one is less than or equal to 4 sigma hk star, and this one is less than 2 sigma hk star, and this one is also less than or equal to 2 sigma hk star. So the summation of them is less than or equal to 8 sigma hk star. And this one, we have also established the relationship between Si and the T. So we have S1 less than or equal to 4T, S2 less than or equal to 2T, and S3 less than or equal to 2T. So we have this one is less than S2T times 8T, and so on. So we can prove that the value of C max sigma is less than or equal to 8 times the makespan for the optimal schedule. So from this result, we can see that the approximation ratio is 8, which is quite loose. So in order to solve this problem by using the gradient pack algorithm, it may not be practical to obtain optimal or near optimal solutions. So in this way, we try to develop a combinatorial Benders decomposition algorithm to solve the problem exactly. So before we start, we first introduce the Benders decomposition algorithm first. So the classical Benders decomposition algorithm, which was first proposed by Benders in 1972. In this algorithm, we suppose that we are given a mixed integer linear program, P, which is described as like this. So minimize cy plus dx and ay plus bx greater than or equal to b, y greater than or equal to 0, and x belongs to some predefined set, big X. And the Benders decomposition algorithm first fixes x bar belong to x, then solve the slave problem SP. So SP becomes minimize cy and ay greater than or equal to b minus b x bar. So x bar is fixed now, and y greater than or equal to 0. And this slave problem can be solved by means of the dual slave problem, SD. And SD by duality theory can be written like this. So if SD has an optimal solution U bar, then we can add an optimality cut Z greater than or equal to U bar times B minus BX can be constructed. And if SD is unbounded, then we can add a feasibility cut 0 greater than or equal to U bar times B minus BX. So for this Benders decomposition method, sometimes it may not be applicable. So for example, when some variables in the sub-problems are required to be integer, then the standard duality theory cannot be applied to derive the classical Benders cut. So based on this, in 2006, Codato and Fischetti, they proposed the combinatorial Benders decomposition algorithm. And this algorithm can be mainly used to handle problems where the MP is a 0-1 integer program, and the sub-problem is the feasibility problem. Means that we have the coefficient C equal to 0. Means here we only have minimized dx, the problem like this. So for such method, they do not use the dual information to generate cut. Instead, they use the slave problem SP as the feasibility check on the system like this. So where X bar is still some fixed variables. So if X bar is not a feasible solution for at least one variable Xj causing infeasibility, then we can avoid assigning the same value of X bar in the future by take a different value from at least one variable Xj bar. And if X bar becomes a feasible solution for the slave problem, then it is also feasible and optimal for the original problem. So this is the main idea of combinatorial Benders decomposition algorithm. And here is the schematic of combinatorial Benders decomposition. And this graph is from the work of Li 2022. So here we start by decomposing the problems into the master problem and the slave problems. And we solve the master problem. Then we check whether the master problem is infeasible or not. If the master problem is infeasible, then we can directly claim that this problem, the original problem, is also infeasible, and we finish. Otherwise, if the master problem we can obtain an optimal solution for the master problem, then we get the corresponding solution, and we can perform feasibility check for all the slave problems. If all slave problems are feasible, then we know that this solution is also optimal for the original problem, and we finish. Otherwise, if there exists one or more slave problems that are infeasible, then we can add the corresponding Benders feasibility cut to the master problem and solve the master problem again. So we continue the process in the loop, and until all the slave problems become feasible. And after that, we output the corresponding optimal solution. So the combinatorial Benders decomposition has been widely used in many problems, and there are numerous applications for this method. For example, for the cutting and packing problems, Cote and his co-authors had considered different problems like a strip packing problem and the two-dimensional bin packing problems, and so on. And the CBD method can also be applied to solve assembly line balancing problems and also other scheduling problems. So in this work, we decompose our problem into the following master and slave problem. As we mentioned before, we know that our problem includes mainly two decisions. The first decision is the assignment of parts into different batches. And the second is the position of parts in each batch. So by the nature of our problem, we decompose our problem into the master problem, which determines the allocation of parts into batches without the two-dimensional packing constraints. So in the master problem, we relax the original problem by removing all the two-dimensional packing constraints from the model. And for the slave problem, we determine the existence of feasible packing solutions for the allocated parts in each batch. So if the packing solution is infeasible for some slave problem, then we generate the corresponding combinatorial Benders cut to forbid the current allocation plan of parts and add such cuts to the master problem. And we continue such process until all slave problems become feasible and output the corresponding solution. So here is the formulation of the master problem. And from this model, we can see that all the two-dimensional packing constraints has been removed. And to strengthen the master problem, we add an area restriction cut here. So this is quite trivial, means that the parts allocated into this batch must, the total area of parts allocated to this batch must be less than or equal to the area of the build platform in the additive machine. And suppose that S equal to UI, B star, and ZB star is the optimal solution of the master problem. So suppose this solution is the optimal solution for this model, and the C max star is the corresponding makespan. Then we denote IB bar as the set of parts that has UIB star equal to 1, means that IB bar is the set of parts that has been allocated by the master problem. So UIB star equal to 1 means that part I is assigned to batch B in the solution of the master problem. Then we solve the corresponding slave problem for each batch B. And note that the slave problem is only used for feasibility check. So the objective function has no effect on solving the slave problem. So we simply put minimize 0 as the objective function here. And all of these constraints are two-dimensional packing constraints. And this is the algorithmic outline of algorithm CBD. So I will not repeat it as the main idea we have introduced. Now we generate different combinatorial Benders cut for any infeasible batch. So suppose that I tilde B is the set of parts that has UIB star equal to 0, and the corresponding slave problem is infeasible. So if a packing generated by the master problem for some batch is infeasible, then we can add one trivial combinatorial Benders cut, which can be described as this one. So the summation UIB for any I belong to this infeasible set should less than or equal to the cardinality of this set minus 1 in any future iterations. So means that by imposing this cut, we can exclude the current infeasible allocation plan from further consideration anymore. And when for this Benders cut, although it is valid, but we found that this cut could be quite loose, especially when the number of parts allocated into such infeasible batch is large. And therefore, we call such cut, Benders cut, as no good cut. And here is an example. Suppose part 1, 2, 3, and 5 are allocated into the same batch by the master problem. And after checking the slave problem, we see that these 4 parts actually cannot be packed feasibly under the two-dimensional packing constraints. So in the future iterations, we will exclude such allocation plan means that we can add a Benders cut like this: U1B plus U2B plus U3B plus U5B should less than or equal to 3. So it means that this 4 variables cannot equal to 4 simultaneously. And then in order to strengthen the Benders cut, we propose another heuristic-based cut, which we call as the next fit-based cuts. So suppose for a given set of parts, we first sort them according to some given order, and then we pack each part subsequently to check its feasibility. And if it is feasible, then we continue to add the parts into the current batch. Otherwise, we obtain an infeasible set of parts, and then we generate a corresponding Benders cut. For example, suppose we have 6 parts, and these parts have already been ordered from 1 to 6. And we put P1 here, P2 here to check whether P1 and P2 can be feasibly packed together into the same batch. If so, we continue to check whether P3 can be packed together with the previous 2 parts. And if it is still feasible, then we consider the 4th part and check whether it is still feasible. So from this example, we can see that after we put P4 into the same batch as P1, P2, and P3, we find that the slave problem becomes infeasible. So P4 cannot be put together with P1, P2, and P3. So we open a new batch and put P4 in the new batch here. And then we continue to check whether P5 and P6 can be packed subsequently. And from this example, we can see that we can generate one Benders cut like this. So for this method, we can see that actually since the old parts have already been ordered and they will be packed subsequently according to the order. So we can only exclude some of the infeasible allocation plans, and still such Benders cut is expected to be not so strong. But for this method, actually we can obtain an up bound on the number of batches to be opened, since after pack all parts, then we can obtain a feasible allocation plan. And the number of batches used by this method obviously is an upper bound on the number of batches.
Han, can you, because we are approaching our time limit, and maybe some people still want to ask questions. So can you?
Okay.
Yeah.
Okay, I will speed up. Okay. So
let's finish in, let's say, 2-3 minutes.
Oh, okay. So one other method that we can use to obtain stronger Benders cut is that we use the method of minimal infeasible subset cut by enumeratively examining all subsets of the parts and check its feasibility. So the method of generating the MIS cut is that we start enumerating each subset of this batch with a cardinality of 2 and check its feasibility. Then we increase the cardinality. Once each time we obtain an infeasible subset, then we generate the corresponding Benders cut. And we also exclude all supersets that include this subset. And we continue such process by gradually increasing the cardinality of subset from 2 to n until no more actions can be made. So here is an example that we first check all possible combinations that with only 2 parts. And if all of them are feasible, then we continue to check the combination with n equal to 3. And for example, 1, 2, 6 are infeasible. Then we know that any superset that include 1, 2, 6 as a subset will be excluded from further consideration, and will generate the corresponding Benders cut according to the infeasible set 1, 2, 6, and generate the corresponding Benders cut here. and continue the process. So such process can output all MIS cuts, but the computational time is expected very time consuming and may not be practical when the total number of parts is larger. So we need to make a balance between the quality of Benders cut and the computational time. So the main idea is that can we generate part of the MIS cut or all the MIS cut for any infeasible batch, not for all the parts. So we propose a different MIS-based heuristic cut. One layer means that we only find the infeasible subset with cardinality n bar -1, where n bar is the number of parts in any given infeasible batch. And the 2 layer, we find the infeasible subset with ns equal to n bar -1 and ns bar equal to n bar -2. And all layers means that we enumerate all infeasible subsets with ns from 2 to n bar. However, for this method, for this MIS-based heuristic cut, we still find that for large size instance, the computation time still remain unsatisfactory. So because of time limit, I will skip here. So we also propose the different accelerating strategies. The first one is that we obtain tighter bounds on the number of batches. And the second strategy is that we introduce a secondary objective. And the third one is that we directly apply the Steinberg theorem to check whether the slave problem is feasible. So we, instead of solving the slave problem by solving the MIP model, we just check the conditions of Steinberg's theorem and check whether they are satisfied or not. And finally, the computational experiments. So the computational experiments, we use the data provided by 2021 and Kuchkok 2019 to generate the data related to parts and related to machine. And we consider 3 different machine types, the small type machine, the medium type machine, and the large type machine. And finally, we consider different combinations of number of parts and the type of machines and generate 120 instances to test the performance of our proposed algorithm. And here are 2 computational results. One is the comparison of performance between different acceleration strategies. So here we can see that if we solve the MILP model directed by Gruber, this instance all of these instances cannot be solved within 2 hours time limit. And by our algorithm, combinatorial Benders decomposition algorithm, we can see that when we consider all the strategies, the computational time is only 80 seconds. So it can greatly reduce the computational time for solving such problems. And the computational time by combining all strategies is only half that we consider the algorithm with no acceleration strategy. And then we also compare different types of Benders cut. For example, CBD0 means that the combinatorial Benders decomposition only use the no good cut, and CBD1 means that we use both the no good cut and the NF-based heuristic method. And the CBD2, 3, and 4 means that we also include the additional 1 layer MIS cut, 2 layer MIS cut, and all layer MIS cut. And then here is the computational result for the same instances. And we can see that the computational time of algorithm with the different Benders cut still much better than solving the MILP model directed by Gruber. And we can also see that the number of master iterations is comparatively greatly less than the master iterations for algorithm CBD0 and CBD1. Means that so CBD2, 3, and 4, they all use some type of MIS-based cut. So we can see that by employing the MIS-based cut, the number of iterations for the master problem reduced greatly compared to these two algorithms. And that's the end of my presentation.
Okay. So yeah, we went a little bit over time. I have some general questions, which I'm not going to ask, for sure not at the moment, because I think there are some specialists in the audience that know your problem and your methods very well. And let's give priority to people like Yossi Bukshin and Chris Potts. And there are many people that can ask more intelligent questions than I can ask. So, okay, Zdenek, can you unmute?
They are already unmuted. So Fabrizio Marinelli is already
So,
raising his hand. So
yeah,
Fabrizio,
any
go ahead.
questions to
Just
Khan?
unmute your mic and go ahead. Huh?
Any questions that people have to Khan?
Do you hear me?
Please go ahead.
Do you hear me?
Yeah, we hear you, Fabrizio.
Yeah, okay. Sorry, I cannot show my face because I have no camera on the desktop PC in my studio. However, my wondering is about this. This problem, it's very simple. If I well understood, is just a two-dimensional beam packing where there are some kind of scheduling issues about the completion time and setup between patterns and so on. I'm wondering if the authors compare their approach with several other approaches that there are in the literature, which are based on dancing wall decomposition and therefore column generation. I know that problems that are very similar to this one can be solved quite good on instances which hundred of parts and non dozens in small times. Maybe it could be the chance to compare the Benders decomposition approach proposed in this talk with some kind of column generation approach that are used in the packing literature.
Yeah, yes, that might be an interesting direction that we can also try to use the column generation method to solve such problems, right? Yeah. But we haven't tried to use such methods for solving this problem right now. Yeah.
Okay, thank you. Thank you.
Okay, Nico Schmidt, please go ahead.
Hi, Tom. Thanks for your presentation. I very much appreciated the approximation algorithm, and I was wondering if you tested it and compared the results in terms of the quality to the combinatorial Benders approach.
Oh yeah. That's a good suggestion. Yeah, I think we should try to also conduct experiments to test the performance of our approximation algorithm. But since this approximation algorithm is quite heuristic, we just greedily pack the parts. So I guess the performance of this algorithm might not as good as the combinatorial Benders cut. But this is a good suggestion. Yeah, it should be done to compare the performance of approximation algorithm. Yeah.
Clearly, it will not be as good, right? But it will be super fast, probably. And your ratio is 8 clearly, but I think in practice it will be much lower than 8. I mean, that's just the worst case ratio, right? Not the actual ratio. And then I have another question, if I may. So you propose to use combinatorial Benders, and I wonder in terms of the implementation, do you solve the master problem and then solve subproblems, or do you solve the subproblems as part of a callback where you add lazy constraints then?
For the both master problem and the slave problem, we solve them by grouping, and we each time solve it, then we add we did not use callback function, but each time we generate, we add it back to the master problem using some iteration to the tech or method using the Python language.
Yeah, because then you solve the master to optimality, right? And then you solve the master to optimality, you solve the subproblems, and only for the optimal solution that you found in the master, you would add a cut or multiple cuts, let's say. But if you solve, let's say if you do the subproblem in a callback, you could also do that for suboptimal solutions. So while you're solving your master problem, you find some suboptimal solutions. And for those, you can already check if they're feasible or not. And you can add the cuts as you go, basically. I think that could be interesting to test to speed it up even more.
Yeah.
Because otherwise, you always have to wait for the master to prove optimality, right?
Yes. So actually, for larger instances, we actually use some other method to not solve the master problem optimally. We actually allow there exist some gaps for solving the master problem. Yeah. But because of time, I do not show them in this slide. Yeah.
Okay. I do have more questions, but I will pass the floor to someone else if someone else has questions.
Anybody else want to ask? Please go ahead. So I will just ask the side question. So the different heights of the objects are treated in master problem. So the allocation of groups that have similar heights is somehow treated there, or how can I perceive that? So why don't you start, for example, from some allocation of parts that is sort of monotonistically decreasing, like starting with the highest objects, going down to the smallest objects?
Yeah, that's the one natural idea, right?
To accelerate a little bit the masters.
Yeah, to sort the parts that with similar heights into the same batch, right? Yeah. Actually, our greedy pack method, although we divided them into different groups, and for each group, actually, we use similar idea.
Yes.
Yeah, we sorted the parts.
So I also use it for the master problem instead of plain ILP to have like warm start, for example, solution or something like that, which will give you some bound or whatever, right?
Yes, the warm up for the master
warm up
problem.
ILP solver.
Yeah.
Okay, so any other questions?
Think about it. Yeah.
Maybe Mike, you wanted to ask some general questions as well.
Actually, my question was actually the comparison with other techniques like column generation, which was similar to the first question that was being asked.
Yeah, yeah, that might be some other direction that to compare the combinatorial band decomposition with the column generation and others. Yeah,
yeah.
But I guess
this is this is a little bit more complicated than an average packing problem. So the level of complexity is going up. So yeah, it would be interesting to make that comparison, because maybe by chance they may be comparable and one may be better than the other. Who knows?
Yeah.
Okay.
That will be some interesting direction. Yeah.
I think we are close to the end. If nobody else wants to ask a question. If not, so thank you very much for your nice talk, and thank you for your discussions. And let me just remind you that in 2 weeks, namely on October 18, we will have a talk by Dirk Briscorn from University of Wuppertal, and he will speak about single machine scheduling with an external resource. Okay.
You know, 2 weeks from now, there will be maybe less people, and we have to go here in the United States. We have to go to Informs.
Okay.
In Phoenix, and so some people may not be available. I will not be available. Actually, I'm that day and that hour on the way back from Phoenix to New York, and usually there are very few Americans at this seminar, so maybe it will not affect the seminar that much, because it's mainly European and the Far East. And there are less of those going to Informs in Phoenix. But at least you know that there is overlap with the Informs conference at Phoenix.
Yeah, so have a nice time at Phoenix. It's a hot city, right? If I remember well. Mr. Conference was there, I think, like 10 years ago. And I hope that all of you will watch it offline then afterwards on YouTube. It's recorded, so don't lose such fantastic topic. And okay, so thank you for watching and being with us, and hope to meet you in 2 weeks. Thank you very much. Bye bye.
Okay. Bye bye.
Thank you. Bye bye.
Thank you. Thank you. Bye bye.